right. So it should be somewhere into here. Okay. Am I okay over here?
Yeah.
So I am deliberately not having you look at things before class today because I want you to look at some of this stuff for the first time. I wish I could be in that same boat myself, but I feel as the professor I should somewhat have an idea of what I'm going to babble about. How many of you have seen or heard of the gamma function? Yes, where? Okay. Everybody here can answer yes. Yes?
Physics?
Physics. We're in physics.
I'm not really sure.
Does show up in physics, shows up in economics, shows up in probability, shows up in sabermetrics. We used it yesterday. So
Is that the error function?
it's not the error function. So gamma of s is the integral from 0 to infinity of e to the negative x, x to the s minus 1, dx, or the integral from 0 to infinity of e to the negative x, x to the s, dx over x. Both are fine ways of writing this function down. And here, s is any complex number with real part greater than 0. Bless you. For us, we're only going to let s be a real number, but you can do this a little bit more generally. I want to do this because this would be a great way for you guys to review Calc 1 and Calc 2 and see some advanced applications of Calc 3. Okay, so you're not going to be tested directly on this. I know that's a very dangerous thing to say before an exam. But by doing this problem, we will get a really good sense of the material we've done and why we care about it. Okay? So, I've given you this function. What values of s would you like to try to get a sense of what is going on?
1.
1. Simplest value, if I put an s equals 1, this vanishes. And we just have the integral of e to the minus x. Okay, so we'll try s equals 1 first. Before we do that, it's worth looking at seeing, does this integral make sense? So I'm going to just very briefly talk about why does this integral make sense. Well, there's two dangerous points when you have an integral like this. Maybe when x is getting close to 0, there's a problem because I have an x to the s minus 1. Maybe that's blowing up. So if s is less than 1, if s is a half, I've got a 1 over square root of x. Is the 1 over square root of x bad near 0? Does 1 over square root of x? Yes. But it's integrable. So the integral of 1 over square root of x dx, this is x to the 1/2 over 1/2. So it's actually okay near 0. Okay? As long as the real part of s is greater than 0, it's okay near 0. So I'm not going to go into too much detail. I'm just trying to give you a rough sense of how you make all this really rigorous. Okay? So we don't have to worry about the integral blowing up because x is getting close to 0. What's the other danger that could make an integral infinite? So one thing was, near x equals 0, things could blow up. What's the other danger?
Multiplying by infinity.
Multiplying by infinity. We're integrating all the way to infinity. Maybe this function is not dying fast enough and maybe things blow up. This is an improper integral. How many of you have heard the phrase or done improper integrals in Calc 2? How many of you have only integrated from 0 to 5 or 0 to any finite number? Oh dear. I'll edit that out later. When you integrate all the way up to infinity, it's an improper integral. Improper integral if go to infinity. And you need to make sure the function decays fast enough so that everything is well behaved. Well, fortunately, e to the minus x is decaying very rapidly. Even though x to the s minus 1 is growing, this is growing polynomially, this is decaying exponentially, everything is going to be fine, the integral will make sense. But you do have to be a bit more careful when you have infinite integrals. And so here's a quick sketch. And this will review things a little bit for sequences and series. E to the x is the sum, n goes from 0 to infinity, of x to the n over n factorial. So this would be less than equal to, greater than equal to x to the m over m factorial for any n. if I look at what's going on here, e to the minus x is 1 over e to the x. When x is really large, I can view this as x to the s minus 1 divided by x to the m. So for large x, say s equals 2014. Okay? E to the negative x, x to the 2014 minus 1 is going to be less than or equal to x to the 2013 over x to the m over m factorial. And the reason is I know e to the x is greater than x to the m over m factorial for any m. All I have to do is choose an m so large that this decays fast enough that the integral will make sense. So what would be a good choice of m to take? What should I take m to be so that I know I will have something that integrates and converges? If I take m equals 1, I'd get 2013 over 1, I'd get x to the 2012. And so I'd be integrating x to the 2012. So, I can integrate from 1,000 to infinity. And I want to put something in here that's going to have enough decay that the integral will make sense. So if I just take m equals 1, I would get x to the 2013 over x to the 1 over 1 factorial dx. This integral blows up. So m equals 1 is too small. I need something bigger than 1. What could I try?
1,000.
So if I try 1,000, I would get x to the 1,000 over 1,000 factorial. X to the 2013 divided by x to the 1,000 is x to the 1,013. That's still growing.
2013 or 2014?
So if I try 2014, I'm getting closer. What's x to the 2013 divided by x to the 2014? It's 1 over x. The integral of 1 over x is natural log of x. I just barely lose. So x to the 2014 is just too small. I should take 2015. And when I do that, this will then be 2015 factorial, integral from 1,000 to infinity of 1 over x squared dx. So when I see what's going on at the tail, it's now decaying like 1 over x squared. And that's enough to give us that the integral makes sense. So again, this is just some of the technical issues you have to be careful about whenever you have integrals. Is the integral well defined? Is the integrand always finite? Well, the integrand here could sometimes be infinity. Fortunately, it's infinity in a fine way. In fact, now you can understand why I say I'm only looking at this function when s is greater than 0. If s was negative, it would blow up too much at the origin. The exponential decay at infinity makes everything very well behaved. Alright, so now it's time to evaluate. So let's calculate gamma of 1. This is the integral from 0 to infinity of e to the minus x, x to the 1 minus 1 dx. Alright, so we're integrating from 0 to infinity of e to the minus x dx. This is negative e to the minus x at 0 to infinity. What is e to the negative infinity? So e to the negative infinity. 0. E to the negative infinity is 1 over e to the infinity. So I get negative 1 over e to the infinity minus 1 over e to the 0. What's e to the 0? 1. Alright, so gamma 1 is 1. Bless you. Alright, now building on our wonderful analysis of gamma of 1, what should we look at? Gamma of 2. So let's calculate gamma of 2. That'd be the integral from 0 to infinity, e to the minus x, x to the 2 minus 1 dx, 0 to infinity, e to the minus x, x dx. Alright, we need a little bit more work to do this. How should we solve this? Yes? Excellent. So we have two choices for u-substitution. Or we have two natural choices. If it's not one of the two natural choices, we're in trouble. The two natural choices are u is equal to e to the minus x, or u is equal to x. Which do you think is the right choice? I'm sorry? So you think u is equal to e to the minus x. And then dv would be... So you're saying u is equal to e to the minus x? And then dv would be... No, if u is e to the minus x, then dv would have to be x dx.
This is integration by parts, not use of
Oh, I'm sorry, you're doing... I'm sorry. You see, I'm just so primed to hear integration by parts, and not u-substitution. U-substitution does not help here. Sorry. Sorry, u-substitution doesn't help. Sorry, this is an integration by parts. Sorry. It does start off with a u, but... Alright. Well, I've already written this on the board. Let's see if this is good for integration by parts. Do you think this is a good idea or a bad idea for integration by parts?
It's your only option.
I'm sorry?
Isn't it your only option?
No, I have two options.
No, I think you should be.
In the words of Yoda, there is another.
You can switch them. Okay.
Right? You can switch them.
Alright.
Right? Yoda's very wise. What is bad about doing things this way? Yes?
When you do the derivative of u, and it's like you're not solving the u to the negative x is going to stay in there forever.
Well, that'll happen even if I do it the other way, but okay, so we have du is negative e to the minus x dx, but the killer is what is v? X squared over 2. So we start off with an e to the negative x times x, and after an integration by parts, we replace the x with x squared. We've increased its power. Bad idea. So what should we do?
Make u x.
Do it the other way. The advantages of being at the blackboard. So if we do it the other way, if we have x and e to the minus x dx, now du is dx, and then v is going to be e to the minus x with a negative sign. So again, this problem is nice that there's only two possibilities, two natural possibilities for the integration by parts. For other problems, it becomes a lot more involved as to what to do. We're very lucky here. And now I like to just go very slowly and write, gamma of 2 would be uv evaluated at 0 and infinity minus the integral from 0 to infinity of v du. By going slowly, I decrease the likelihood of making a mistake. Alright, this is equal to uv, which is negative x e to the minus x at 0 infinity. The minus and the minus becomes a plus. The integral from 0 to infinity of e to the minus x dx. Alright, when I plug in infinity, what's x e to the minus x? So I have infinity times e to the negative infinity. 0. How do I actually figure that out? So I'll have to put this as an aside. Y is the limit as x goes to infinity of x over e to the x equal to 0. I will accept a one-word solution. You got to remember something from a calc class. L'Hopital. And there's some accent marks somewhere in the name. Okay. L'Hopital's rule. If I take the derivative of x is 1, the derivative of e to the x is e to the x, we're fine. So when I plug in x equals infinity, even though I have infinity times 0, it's an infinity times 0 I can understand. When I plug in 0, what do I get? 0. Now I have the integral from 0 to infinity e to the negative x. We just calculated that. What do we get? 1. So gamma of 1 is 1, gamma of 2 is 1. By induction, gamma is always equal to 1.
Sorry, what was the second step we just did?
This one over here. This is the calculation we've already done earlier.
Okay.
So we did this above. So can I claim just because I tried two values of s and it equals 1 both times that it's always equal to 1? No. Okay. So we should bless you. We should try some more values.
Thank you.
In the interest of time, I will just write down a couple of the values for you. 1, 1, 2, 6, 24. And if you think about it, it shouldn't be too bad to get these. I just keep integrating by parts. Anybody recognize these numbers? I'm sorry?
Factorials.
They're factorials. So if n is a positive integer, gamma of n is n minus 1 factorial. And this leads to the wonderful convention that the gamma function is shifted from the factorial function by 1. Right? It turns out that this is a more convenient definition for certain problems. There is another function defined, instead of calling it gamma of s, it's called g of s. And what nice property do you think g of s has? So gamma of n is n minus 1 factorial. What do you think g of n is? Just n factorial. So the g function is just a small shift from the gamma function, so you don't have this, pesky minus 1 that you have to remember. What I want to do is I want to prove gamma of n is n minus 1 factorial. And by proving this, this is a great way to review integration by parts again. It's a great way to see applications of calculus. And then we will shift to trying to find other values of the gamma function. What's nice about this is a generalization of the factorial function. If I can show it equals n minus 1 factorial whenever n is an integer, I can now talk about what does it mean to take 1/2 factorial. Now if you think about it, what does 5 factorial mean physically? Yes?
5 times 4 times 3 times 2 times.
Okay. And then what's my representation? If I had to tell a story, what am I doing if I'm doing 5 factorial?
You're multiplying by each integer that goes into it.
Okay, that's how you do the computation. Can you tell me what you've computed? What does 5 factorial represent?
All the possible outcomes of 5 different.
So if I have 5 different things, I want to look at the ordering of them. If I have 5 different people and I have 5 different offices, it's the number of ways of assigning the offices to the people.
And order matters.
When ordering matters. So president is different than vice president is different than secretary. What does it mean to have 1/2 factorial? How many ways can you order half a person? What does it mean to have negative -1/2 a person? And ask how many ways can you order negative -1/2 a person? It turns out this actually matters in higher mathematics. And so we will see applications of this, and I will connect it with Calc 3 before the day is over. So this is just a great way to review for the exam, while at the same time seeing where all this material goes. Alright. So I will keep the definition of the gamma function on the board. And what I'm going to do is I'm going to state an identity. So theorem, gamma of s plus 1 equals s gamma of s if s is greater than or equal to 0. So what this does is this tells me how to evaluate the gamma function at new places given its value in old places. Or if you want, you could even do if s is greater than or equal to -1. So, or s greater than or equal to -1. It's a way to extend the definition. So right now I can understand the gamma function if s is a positive number. There is a reason why I want to talk about things like -1/2 factorial. We will get to that later today. If I put in s equals -1/2, I get gamma of 1/2 over here. Well, that's fine. I have an integral for it. And I get gamma of 1/2 is 1/2 times gamma of -1/2. We will actually be able to talk about something like this. The proof is not that bad. We've actually already done it. Gamma of s plus 1 is the integral from 0 to infinity of e to the negative x, x to the s plus 1 minus 1 dx. I'm just substituting in. This is the integral from 0 to infinity, e to the minus x, x to the s, dx. Let's do integration by parts again. U is equal to x to the s, dv is e to the negative x, du is s, x to the s minus 1, v is negative e to the minus x. And when we put everything together, we get gamma of s plus 1 is uv at 0 infinity minus the integral of v du, 0 to infinity, which is going to be negative x e to the minus x, I'm sorry, x to the s, negative x, e to the negative x at 0 infinity, plus the integral from 0 to infinity of e to the negative x, s, x to the s minus 1 dx. L'Hopital again, this is going to be 0. 0 by L'Hopital. What is this expression equal over here? It should be very similar to something on the board.
The original formula function.
Almost the original. This
Oh, plus an s.
times an s. Plus an s in terms of appending s to the expression, yes. So this is then just equal to s gamma of s, which completes the proof. So really, the argument we did before, when we proved the value of gamma of 2, by just looking at things a little bit more formally, that also gives us gamma 3, gamma 4, gamma 5. We get gamma of s plus 1 is s gamma of s. And so now we can just walk through and get all the different factorials. And so just because it's nice to kind of see, let's just do it slowly. So we know gamma of s plus 1 is s gamma of s, and we know gamma of 1 is 1. So gamma of 2 is going to be gamma of 1 plus 1 is 1 times gamma of 1 is 1. What about gamma of 3? We can write that as gamma of 2 plus 1, which is 2 times gamma of 1. Which is
2.
2.
But it shouldn't be 2r of 2, which would be the same
Yeah.
thing because...
So the question is, which way do we want... sorry, so it should be 2 gamma of 2. Thank you. 2 gamma of 2. Thank you. Gamma of 4. It would be gamma of 3 plus 1 is 3 gamma of 3 is 3 times 2 is 6. Gamma of 5 is gamma of 4 plus 1 is 4. Gamma of 4 is 4 times 6. And here's my 24 factorial. So 24. There's my 4 factorial, my 3 factorial, my 2 factorial, my 1 factorial. We've actually mentioned 0 factorial is 1. There's one way to do nothing. Okay? Alright, so far so good. We've calculated this gamma function. It's not entirely clear why we want to do this. The hope is that this is very useful. It takes the factorial function and converts it to an integral. And maybe now we can actually use calculus to understand things about the factorial function. Turns out you can do this in upper level probability in math classes. We have actually seen in some sense a situation where we need to know one of these values. And this is going to provide an alternate way of doing it. So, after understanding gamma of 1, gamma of 2, gamma of 3, we understand gamma at all positive integers. What's the next natural place to try to understand the gamma function? We can kind of get the negative numbers just by using our identity. So it's really not any different than here. So we need a different type of number. non-integer. So give me a non-integer. What's the simplest non-integer you can think of?
5,
I'm sorry?
0.5,
0.5, or 1/2.
1.
That is the best one to look at. So gamma of 1/2, how do I write gamma of 1/2? This is gamma of, I'm going to do it very carefully, of negative 1/2 plus 1. No, I'll leave it like this. So I'm going to put the equal sign in quotes. This should be 1/2 minus 1 factorial. It's the generalization of the factorial. Gamma of n was n minus 1 factorial. So gamma of 1/2 should be 1/2 minus 1 factorial. And it turns out this is equal to the square root of pi. This is quite strange. How many of you have been in a large class that's graded on a curve? Yeah, I was going to say more hands should be going up at this point. Lots of large classes grade on curves. This allows professors to grade you on a curve. The fact that this is the square root of pi. So if you don't like the bell curve and Gaussians and normals for grading, this is whom to blame. Alright? Let me show you how this comes into play. So we don't need that identity anymore. I'm going to keep the formula for gamma of s up on the board. We showed earlier that the integral from 0 to infinity of e to the minus x squared over 2 dx equaled the square root of pi. We showed this. How do we show this? Who remembers? How do we calculate this? This is one of the strangest proofs I think we've seen all semester. How did we get that this equaled square root of pi? Oh, I'm sorry. I think we did it without the 2. I think without the 2 was square root. Yeah, we did without the 2. How do we get that this equaled the square root of pi? I'm sorry?
Did you make it into a multi?
We made it into a multi-integral. We multiplied it by itself, wrote it as e to the minus y squared, combined them, shifted to polar, and used the polar change of variable formula. Which is a very strange way to approach this integral. This is a one-dimensional integral, and we're bringing it up to a two-dimensional integral. And we used this to then get the integral from 0 to infinity of 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared equals 1. So for probability density, this integrates to 1. This allows people to use the bell curve to grade you. Alright. I want to show you how this is related to the gamma function and then talk about how to evaluate this. And again, the purposes of this is twofold. I want you to see where the material we use comes into play, and I want to review all the stuff we've been doing this semester. Alright? So we can go in one of two ways. I can either start with the gamma function and go here, or I can start here and go to the gamma function. Which way do you want to go? Makes no difference. Your choice will affect 11 o'clock. From here to here or here to here? Which way?
Bottom one.
Bottom up, okay. So, let u equal x squared. So what is du going to be? If u is x squared, du is
2x.
2x dx. So dx equals 1/2 of du divided by x. Well, x is equal to square root of u. Oh, shoot. Sorry. This integral is supposed to be from minus infinity to infinity. Sorry. Okay? So, I want to do this because this is a very common mistake to make. What's the range of u? x goes from minus infinity to infinity, what does u go from?
Minus infinity to infinity.
U goes from infinity to infinity. This doesn't seem right. This is a chance to review a very subtle issue that often happens in Calc 2. When you're doing your u substitutions, you have to make sure you have a one-to-one function. That each value of x corresponds to one value of u, each value of u corresponds to one value of x. Here, two different values of x correspond to the same value of u. This is a problem. Should this integral be the same as the integral from infinity to infinity of some? No. The problem is that when x is negative, it's really the same as when x is positive, and I'm double counting things. And so when I do my u substitution here, this gives me the integral from infinity to infinity. Okay? How can we fix this? We can use symmetry. This is the same as twice the integral from 0 to infinity. Okay? We had some homework problems on this where if you integrate an odd function over a symmetric region, it's 0. If you integrate an even function over a symmetric region, the integral is just twice the integral from 0 to the endpoint. So if I do that, I now have x goes from 0 to infinity becomes u goes from what to what? 0 to infinity. And now everything is well behaved. So we get 2 times the integral from 0 to infinity of e to the minus x squared dx is equal to 2, I'll write this as x goes from 0 to infinity, u goes from 0 to infinity, e to the minus x squared becomes e to the minus u. Dx becomes 1/2 square root of u in the denominator. Square root of u in the denominator is the same as u to the minus 1/2. Right? Everyone agree this is the same as u to the minus 1/2? I'm going to write minus 1/2 as 1/2 minus 1. Is this a fine way of writing negative 1/2? Why the hell would I want to write minus 1/2 like that? Yes?
Because 1/2 is s.
Good, because now 1/2 is s. My definition of gamma is e to the minus x, s to the s minus 1. S is now equal to 1/2. The 2's beautifully cancel, and there's gamma of 1/2. So we've just shown that gamma of 1/2 is square root of pi. Okay? This is strange. And so again, if somebody ever says, how many ways can I order negative 1/2 of a person? You now know the answer. I doubt you will actually ever be in that situation where you will use it directly, but this is one of the whole points of mathematics, and we will see this when we get to sequences in series. Some of you have already looked at the video. There was this physicist where you add all the positive integers and you get negative 1/12. These strange things actually have physical interpretations. And so right now we're also laying the groundwork for a chapter, well, I guess we're not doing the book anymore, for the unit on sequences in series. And so this idea of taking things that you know and using them in other regimes is going to be extremely powerful. And so we can interpret something like negative 1/2 factorial as the square root of pi. This is extremely important. It comes up with the Gaussian. So it relates the Gaussian and the gamma function. This is not the only relationship between the two of them. There is a lot more. Given the fact that I only have about 11 minutes left, and I have 12 minutes left, I have to prioritize, and I don't want to go into some of the other stuff. I want to make sure I can finish the other stuff. Yes?
So where did the 1 over the square root of u come from? In the
Sure, u equals x squared, so du is 2x dx. So that means dx is du over 2x. Well, I don't want to write x down underneath the u. What does x equal? If u is x squared, x is the square root of u.
Okay.
So I've got dx is 1/2 du over root u.
Okay.
And now by using that, I then just write the square root of u as u to the 1/2 minus 1. So, strange stuff here. Other questions on this? Okay, what I want to do now is I want to show you a little bit more about the gamma function. I want to show you some of its connections with probability, and I want to use this as a way to review Calc 3. Okay? So again, for those of you who don't care about applications, I hope you will at least bear with me and use enlightened self-interest. Right? That what we're going to see will be a great way to review stuff for the exam. But in such a way that I can justify to myself, spending class time on it. And this is the advantage of having the flipped classroom, is it gives us extra time to have more reviews for exams like this because we've done some of the material. And so now, what I want to do is I want to talk about the beta function. So here, a and b will be greater than 0, and gamma of a, gamma of b is gamma of a plus b, the integral from 0 to 1 of t to the a minus 1, 1 minus t to the b minus 1 dt. Just going to make sure I've written this down correctly. Yes. This is a beautiful relationship. It relates values of gamma at a and gamma of b to a value of gamma of a plus b, and a nice integral from 0 to 1. Another way of interpreting this is, if I divide both sides by gamma a times gamma b, what does the left-hand side equal? So if I divide by gamma a, gamma b, the left-hand side is just 1. I get a probability density. I get a beta distribution. The beta density is going to be gamma of a plus b over gamma of a, gamma of b, t to the a minus 1, 1 minus t to the b minus 1, 0 less than equal to t less than equal to 1. For those of you who are taking economics, you might see the beta distribution modeling a lot of things. It's going to give you curves that can look something like this on 0, 1. So it gives you a great family of one-bump distributions. A lot of natural phenomena are modeled by this. Well, if I have a non-negative function that has a finite integral, if I just rescale it so that it integrates to 1, it's a probability density. Why do we care about integrals? Why do we care about areas under curves? What word makes me happy? Probabilities. So if I give you a non-negative function that integrates to a finite number, I can rescale it and make it a probability. And so it turns out that the way you rescale it is you multiply by gamma of a, gamma of a plus b over gamma of a, gamma of b. So what we have to do is we have to show this equality. Once we show this equality, we're done. Okay? So the difficulty is, how do we show an equality like that? Alright, so as always, I will start with the definition of the gamma function. I'm going to look at just the left-hand side, and I will show after a lot of change of variables that the left-hand side equals the right-hand side. I will send you the chapter on a book that I'm writing with all of this calculations, everything from today's lecture done in full detail, so that if you want to see it, by all means, it will be there. The idea is I want you to get a sense of where things are used, and get a sense of how you use Calc 3, and just review what we've seen. Alright, so gamma of a, gamma of b, I'm going to originally write it in a poor way, and then you'll tell me how to fix things, is the integral x goes from 0 to infinity, e to the negative x to the a minus 1 dx, integral x goes from 0 to infinity, e to the minus x to the b minus 1 dx. It's not wrong, but what's bad about this? I've used the x twice. So instead of using x twice, what should I do? I should use y. So again, very easy. I just erase a little bit on that, and the x's become y's without too much trouble. It's very convenient. Alright, we're back to Calc 3. We have a double integral. 6 minutes to go, we finally get a double integral. I will give you a clip. Cameron is probably about 2 years old, and he will teach you what to do when you see a double integral. What should be your first thought? If you have a double integral that's hard to do, what should you do? Switch sums. Switch orders. Okay. Will switching the orders of the x and the y integration help us? No! Why not? They're the same thing. So if I switch the order of integration, it does not help. We need to somehow introduce an asymmetry. This is the integral y goes from 0 to infinity, integral x goes from 0 to infinity, e to the minus x, e to the minus y, x to the a minus 1, y to the b minus 1, dx dy. I just want to make sure I'm doing it in the same order as the book. Okay, good. I've got x coming first. Or do I switch down on me? Yeah. Okay, so if I switch as is, this is not going to help us. Right? I somehow have to do something to get an asymmetry. What can I do to get an asymmetry? Well, let's look at how things are going. I've got x's and y's together. So one good thing is to actually write x in terms of y. And so here is a very non-standard change of variables. X equals y times u. I need to do something. So this is an advanced topic right now. I want to give you a sense of how you attack more general, more difficult problems. We've talked about the big three change of variables. We've talked about interchanging orders. Well, there are times when interchanging orders won't help you. If you have something that's very symmetric, if you interchange orders, you can't take advantage. We've seen problems in class where if we do them in one order, it's difficult, but if we do it in the other order, it's easier. I have to introduce an asymmetry. So let's let x equal y times u. What will dx be? Dx would be?
dy du. I'm sorry.
What is
Not-
the complement?
Well, you've got to think, which is my new variable? X equals y times u. I fixed y, I'm integrating with respect to x. So y is fixed. So dx would be y du. And as x goes from 0 to infinity, what does u go from? So if x goes from 0 to infinity, y goes from, y is fixed, so u goes from 0 to infinity. So this is the same as the integral y goes from 0 to infinity, integral u goes from 0 to infinity, e to the negative x, e to the negative, this is e to the negative y times u, e to the negative y. After you do some algebra, it's 1 plus u times y. X to the a minus 1 becomes y to the a minus 1, u to the a minus 1. So u to the a minus 1, y to the a minus 1 times y to the b minus 1 is y to the a plus b minus 2. But now dx becomes y du, so one of the y's comes over here, and after you do the algebra, you get du dy. Okay? So again, it's just algebra getting from this line to this line. Okay. Does this look more complicated than what we started with? That's a good thing. What can we do now? Now we can switch orders of integration. Right? We had to desymmetrize it first. Now switching orders of integration is non-trivial. If we switch orders, let's look at what the y integral looks like. Ooh, I've got a y to the a plus b minus 1. What does it look like? Looks like? Almost looks like a gamma function, except, my s is looking like a plus b, that's good, but I should have an e to the negative y. I've got an e to the negative 1 plus u times y. Another change of variables. Let's replace y with y times 1 plus u. I have to switch orders of integration first before I can do that, but I will then be able to set this up and get a beautiful gamma integration. So now we get the integral u goes from 0 to infinity, integral y goes from 0 to infinity, and now we will have u to the a minus 1, e to the negative 1 plus u times y, y to the a plus b minus 1 dy du. And now we change variables. So we want to replace y with 1 plus u times y. So let's let y equals 1 plus u times t. And now what would dy equal? It would just be 1 plus u times dt. Okay? And so now if I plug things in, I get the integral u goes from 0 to infinity. What's my range for t? When y equals 0, t equals 0. When y equals infinity, t equals infinity. I've got a u to the a minus 1. I have an e to the minus t. Y becomes a 1 plus u to the a plus b minus 1, t to the a plus b minus 1. dy is 1 plus u dt. And now what you can see is, when we pull everything out, the t integral is going to just be a gamma of a plus b. So, t integral gives gamma of a plus b. And so I'm not going to finish the rest of the calculation. The rest of the calculation is in the notes that I'll send to you. I want you to get a sense of how you can use this stuff. This idea of switching orders of integration, this is not just a trick to give you more cookbook problems. This is one of the only ways we know how to evaluate a lot of very difficult integrals. Okay? So this is a great way to see all the stuff we've done and where it goes. Another good way to see where it goes is to come to class on Friday and take the exam. Okay? So again, none of this material will be directly on the exam. I'm not going to give you a gamma function problem. I'm just choosing this as a way to show you what's out there.